We're going to start to really do the flipped classes now. And so I am not going to go through all the details of the notes. What I'm doing is I'm doing a slow transition. As the semester progresses, I'm going to do less and less of what you're watching online. This is a chance to start getting a sense of what's going on. What I want to do today is I want to start with coordinate systems. So right now we've seen a simple example with Manhattan versus Boston. Right? This is the situation where New York City wins. Okay? But Boston, Boston's bad. Right? It's a curvilinear coordinate system. It's not even at least slanted. Slanted is not so bad. Different problems have different natural symmetries. And what I want to do today is show you that certain problems are more natural in different coordinate systems than the standard XY coordinates you're used to. Some of these I hope you have seen before. If not, please give me the names of your algebra teachers. I need to send them a letter. Okay? How many of you have seen polar coordinates at some point in your life? Okay, good. So the first is polar. So x equals r cosine theta, y equals r sine theta, 0 less than r less than infinity, 0 less than equal to theta, and I'll say strictly less than 2 pi. But of course I could go over 2 pi. The problem is, when I use polar coordinates like this, there's not a unique way of representing some points. So if I increase my angle by 2 pi, the cosine and the sine are the same. So if you want to graph it, here's the point xy. This distance is r, and this angle is theta. It's just a different way of representing the point. And so the way we get these relations is using trig. So whose theorem are we using? Pythagoras. So relations by Pythagoras. Sounds like a designer. Right? Relations by Pythagoras. Okay? We are milking Pythagoras for as much as possible. So if I give you something in xy space, can we figure out what r and theta is? If I give you r and theta, is it easy to figure out what x and y are? Sure. I tell you what angle to move at and how far to travel. Well, it seems like you should be able to go the other way around. If I give you x and y, you should be able to figure out r and theta. So the question is, how can we isolate various things? Well, the biggest thing with Pythagoras is cosine squared plus sine squared is 1. That's what you get with the right triangle. So if we drop things here, this is r cosine theta, this is r sine theta. And so Pythagoras tells us, let's look at x squared plus y squared. And we get x squared plus y squared is r squared cosine squared theta plus r squared sine squared theta, which is just r squared. Okay, so we get r is the square root of x squared plus y squared. We're never allowing r to be negative. For us, r is the distance, a positive distance from the origin. All right, now we want to get theta. And so, well, if we know the two sides over here, if we take their ratio, that's the tangent of theta. So tangent of theta is y over x is r sine theta over r cosine theta. And you can see the r's cancel. Well, if this is the tangent of theta, then the arctangent or the tangent inverse will give us theta. So some people write arctan of theta is going to be, arctangent of y over x is the end of theta. I apply arctangent to both sides. Some people prefer to write tangent inverse of y over x equals theta. Can somebody give me a reason, and I'm a Bostonian, so arctan is not easy for me to say, why do I still say arctan rather than tangent inverse?
Some people might think to just flip.
Yes, some people might think this is 1 over tangent. This is not equal to 1 over tangent of y over x. And that's why we don't like this notation. We like to use arctangent because we can quickly look at this and now see, bless you. Oh good, it's not my spot. We can now see that it is the inverse function and not the 1 over function. Okay, so this is polar coordinates. Any questions about polar coordinates? So now if I give you a point, you can calculate. If I give you an xy and r theta, doesn't really matter. You can pass back and forth. Later today, I'm going to show you some programs I've written in Mathematica that use polar coordinates, that use ideas of circular motion. How many of you have ever studied, ancient Greek math and physics? They believed the circle was the perfect shape, at least for the orbit of the planets. And they believed all planetary motion must be circular. Now, there's a problem with that. What's the problem? It's not. It is amazing how well they did in describing the orbits of the planets just using circles. And so I will show you later how to use polar coordinates to do a phenomenal job describing the orbit of the planets. Okay, after polar coordinates, what do we do next? Cylindrical. This is where it's really nice to be the professor. I can just go, I can erase polar, I can write cylindrical, and I just have to add z equals z. And then I come over here, and I have to add z equals z. That's cylindrical coordinates. The only difference between polar and cylindrical is in cylindrical, it's like this piece of chalk. You can go up and down. You're going in a circle in the xy direction, and then you're just sweeping out what the circle does. So really there's not much difference from cylindrical to polar. The real killer is when we get to spherical. And I always have to check my notes as to how to do spherical, because the mathematicians and the physicists sometimes have different notation. And this is one of the situations where they have different notation. I learned things from the physicists. They do things with a different notation here. I will try to do things with math notation. Does it matter what I call my variables? No. Could I call this, instead of calling it r, could I call it gamma? Yes. I would confuse people. Okay? When you look at different books, and I strongly urge you to look at other books whenever you're taking a class, don't just look at one textbook. Look at several. Different books use different notation, and it can be confusing to go back and forth, especially if you go from a book written by mathematicians to a book written by physicists. How many people have taken a physics class? Right. The worst notation I've ever seen in my life was from a physics book. Have I shown you this? P equals mf. This is a famous equation from physics. Any thoughts? I'll tell you what any of the three letters means. What letter do you want to know? P is force. Acceleration.
Oh.
This is force equals mass times acceleration. This holds the record as the absolute worst notation I've ever seen in my life. Okay? It is not wrong to use P for force and F for acceleration. I dropped that book and returned it immediately to the library. Right? It's, as long as you define what you're doing, you can do that. I don't advise it. Alright, coordinate systems. So let's do the last one. So the last one is spherical. So spherical is the more interesting one. So I'm trying to draw a circle here. There's the equator, and there's my origin. Here's my z-axis coming straight up. Here's my x-axis going this way. My y-axis is going perpendicularly like that. Okay? How many coordinates do I need to describe where I am on the surface of the sphere? 3. And the standard coordinates that you're used to using are? X, Y, Z. We're going to use rho, theta, phi coordinates. Rho is going to represent the distance to the surface of the sphere. So rho is going to be the radius. What letter would you like to use for radius?
R.
R. Right? There is a reason we're using rho. It is not because I am from Boston. Okay? We're going to save R for later. Where have you used R? Polar. We're actually going to use polar coordinates in describing what's going on in the sphere. And so we're going to save the R for later. And so that when we use polar coordinates, we'll be able to exactly use something we've done before. Okay? That's why we're holding off on this now. So again, right now we're putting a lot of material in the bank. Later we're going to want to do integration. And after I explain spherical coordinates, I'm going to show you a little bit of a teaser as to why these coordinates are so good. Okay? So let's imagine we're somewhere on the surface of the sphere. So I have to choose some way to represent my angle coming down from the z-axis. And then I spin around somewhere up and through here. So I have two choices, theta or phi. So who read the notes? Do we use theta or do we use phi? What do you think, Kayla? What's your middle name? Sophie. What should we use? Phi? I wanted to spell her middle name S-O-Phi, special orthogonal with an angle of phi. It's a 2x2 matrix. I was outvoted. But today, in honor of you, we will do Sophie. So we're going to do you first. We're going to put you there, okay? So we're going to come down phi. And then once we come down phi, we start off at the x-axis, we start off in the same direction as the x-axis, and we move over theta radians. Okay? So we come down phi, and then we move over theta. So this is going to be parallel to the xy plane. This is going to be coming down from the z-axis. Okay? So the first thing is we have to figure out what is our z component. Well, if this is an angle phi and the radius is rho, how much is the z component going to be? So we've got a triangle. What's the z component going to be? I'm sorry?
Sine of phi.
So sine of phi would be this length over here.
Cosine.
So it's going to be cosine of phi. So z is going to be rho cosine of phi. Okay? But it's not bad that you said sine of phi, because we're going to need that. That's going to come up here. This is going to be rho sine phi. I need a name for that. What letter should I use to denote rho sine phi? Any thoughts what letter I should use? I think I heard somebody say it. Ah! Right? Because now I'm in a circle. I'm in a circle parallel to the xy plane. I'm just at a height of rho cosine phi. So, in a circle of height rho cosine phi, of radius rho sine of phi, which we will call r. Well, now we can do polar coordinates. In polar coordinates, I just need to know the angle and I need to know the radius. So I now get x is going to be r cosine theta. So that's going to be rho sine phi cosine theta. Y is going to be r sine theta, which is going to be rho sine phi sine theta. And just for good measure, let's just recall that z is rho cosine of phi. What should be true, because this is a point on the sphere? What should be true about x, y, and z because it's on the sphere? So a circle of radius r is all points is all points r units from the center. What do you think a sphere of radius rho is? So a sphere of radius rho is all points that are rho units from the center. So how far should this point xyz be from the center? It should be rho. So as a check, do algebra and find that x squared plus y squared plus z squared square root equals rho. Right? I'll leave the algebra to you. It's a good exercise to just go through this and check. You know, I'm on the surface of a sphere, radius rho. My distance from the origin should be rho. You know, when you do the algebra, that's what you get. All right, we haven't quite reached the beginning of chapter 12 yet, but in chapter 12, which you've all read and loved, it talks about defining functions and knowing where they're defined. What's the inputs? We should talk about the inputs. What are the possible values for rho, for theta, for phi? What are the possible values for rho? So what could rho take on?
All real numbers.
So that would mean I could have a rho of -3.
All positive.
Almost. You're missing something. I could have a circle of radius. I could have a sphere of radius 0. I could be at the origin. So when you're trying to figure out where could you be, 0 less than equal to rho less than infinity. Right? Now let's think about phi. So phi is how far we come down from the z-axis. How far down could we come from the z-axis? You know, let's measure things in radians. So pi over 2 just comes down to the x-axis. I'm sorry?
Can you go all the way around?
So over here is pi. Now you want me to keep going? This is really painful. Is it enough to just stop over here? And I really hope so. Why is it enough to stop here?
You could just go to him and the other way.
Right, because, well, I could do negatives, but the other thing is I have my theta that I'm going to be spinning around. So once I come down a certain amount, I then spin around in a circle. So I can get this point by coming down here and spinning. If I come down here and spin, I can get this point. So I only need phi to go all the way down to pi. So 0 less than equal to phi less than or equal to pi. And what about theta? 2 pi. 0 less than equal to theta less than 2 pi. So these are the possible values for rho, for phi, for theta. These are the ranges for this problem. I'm not going to write them down, but you should do as an exercise, how would you find rho, theta, phi if I give you x, y, and z? Well, we've already done how to find rho. Rho is just the square root of x squared plus y squared plus z squared. Similarly, figure out how you would determine what is phi, how would you determine what is theta. Some of them will be easier than others. Which do you think would be the easiest one to get next? Why theta? So for theta, if we just take the ratio, the rho sines phi will cancel. We'll have a tangent as before, so you can solve for theta. Not a problem. Theta is a good one to do next. Phi isn't horrible. You could have an arc cosine and get that, or try other ways as well. Okay, so I'll leave this as an exercise. Now, one thing to worry about is if rho equals 0, if I'm at the origin, what values of phi and theta should I take? So if rho equals 0, or if x, y, z equals 0, if I'm at the origin, what do I take for phi and theta? So I could take 0 for both. Anything. This is the problem. These change of variables break down at the origin. At the origin, any angled choice matters. So, I don't move at all. Any spinning I do is fine. I'm still going to be at the origin. So unfortunately, these coordinate systems are not unique at the origin. Everywhere else it's unique. You give me an x, y, z that uniquely specifies a rho, phi, theta. You give me an xy that uniquely specifies an r theta, except at the origin. Fortunately, in all the stuff we're going to be doing, that one bit that one little issue is not going to matter in the integration, because it's only a point. Okay, so fortunately we're going to be okay, but you should be aware that these transformations break down at that one point. Okay, I want to now just briefly motivate why we are going to be doing all this and why we're going to be caring about all of this. Has everybody seen a basketball, a baseball, a tennis ball at some point in their life? You've all seen an example of a sphere. These are really good shapes. Give me a sport where the shape is not as good.
Football.
Football, right? We will actually learn how to study the football by understanding the sphere. And you can essentially understand the football by understanding the sphere. It's one of my favorite integrations. What I want to do now is I want to explain why we care. So, in several variables, when you integrate, often a choice. One is a good function, bad region, or two, a bad function and a good region. So you can either have a complicated function over a very nice region, or a very nice function over a very bad region. You haven't done Calc 3 yet, it's not clear which one is going to be better. It turns out you want two. Typically this is better. So in XY space, can somebody just with their hand show me what a circle looks like? Good, thank you for using those fingers. Okay, so we will draw a circle like this. What do you think a circle looks like in R theta space? What shape does a circle look like in R theta space? So here's, my filled in circle. What do you think a circle looks like in polar coordinates? I'm sorry? Okay, so if I do just the boundary of the circle, okay, a line, so good. What would the line be?
It would be a horizontal line at R through this.
Excellent. And so if I then have the whole filled in circle, I just have lots of circles of different radii, 0 to pi. This is what a circle looks like in polar coordinates. It turns out it's very nice to integrate over rectangles and boxes and stuff like that. And so the whole point of these coordinate changes is you convert your region of integration to being something very nice. And it's going to make a lot of the issues vanish. I'm not going to do the calculation. What do you think a sphere looks like in spherical coordinates? What do you, square's two-dimensional. Cubish. So a sphere is a box in spherical coordinates. So as a nice exercise, sketch what a sphere looks like in spherical coordinates. Okay? And so this will have enormous dividends. We're changing what the region looks like. Is this still a circle? If I look at it over here. Does this still represent a circle? Yes. I'm just representing it in a different way. Okay? It's a way that's going to be more amenable to certain calculations that we need to do. Okay? So again, this is material in the bank already. Alright, this finishes chapter 11. Any questions before we start chapter 12? Alright, so this means it's time for an exam. Alright, so there will be no new material from this point onward that will be on the exam next Friday. Okay? The only material on the exam is material up to and including what we just did a minute ago. Alright, it'll be chapter 11, it'll be some calculus problems. Okay, that's it. What we're doing now is we're starting chapter 12. So there are two main themes in this class. What are the two main topics we're going to study?
Partial derivatives.
Partial derivatives, and the other? What else will we do? Yes?
Triple integration.
Triple integration, n-dimensional integration. So you often split derivatives and integrals into Calc 1 and Calc 2. We don't really have Calc 3 and Calc 4, we just do them all. The reason is, essentially everything you've done in Calc 1, so much of it generalizes. So you've already got a huge amount of it already done. What I want to do is I want to emphasize the new ideas that come into play. I want to emphasize where the Calc 3 lies, where's the new geometry. There are some differences in higher dimensions. Okay? If I want to walk, I'll move the chair here. Let's say I live in a one-dimensional world and this chair is in that same line as me. And this chair is completely nailed down to the floor. Can I walk to the wall? No. You know, I'm stuck here and I can't do it. In 2 dimensions, can I walk to the wall? Yeah, very easily. Just say, hello. Just detour a little bit around it. Not a big deal. Geometry changes greatly in several variables. You have a chance of taking detours. The whole notion of limit is very difficult. And it's very different than what happens in 1 dimension. So Kayla, are you doing more of the swirlies? Or are you doing coloring? Oh, okay. Kayla is working hard at making swirlies for everyone. How many of you have seen the Karate Kid Part 2, where he goes to Okinawa? Yeah, where they learn the secret of karate. Kayla is working on the swirlies, which is the secret of Calc 3. Right? She will eventually have enough so that everyone will get a personalized swirly. And they're being numbered, just like real artwork, so that you know which one you have, and they're being signed. Okay? There is a huge difference between Calc 3 and Calc 1, Calc 2. But once you understand that one hump, everything else becomes very similar. What I want to do now is I want to talk a little bit about what we're going to be doing in Chapter 12. So, the real issue is, what does it mean to look at functions of several variables? So you've hopefully seen things of several variables before. So this is now Chapter 12. So we'll study functions of several variables. One of my favorites is from chemistry or physics. PV equals nRT. Pressure times volume is the number of moles, the universal gas constant times the temperature. And so you can solve for any one of them in terms of the other. So this is a function of several variables. Another thing you could have as a function of several variables is I've done work in the movie theater industry for theaters as to try to maximize their profit. And that profit is going to be a function of several different things. You know, the time of day you show the movie, what type of movie it is. You know, is it a kid movie where a lot of people are going to be coming in and buying, you know, food? It's going to be a cost of also how much are you going to have to spend on cleaning up. How long has the movie been out? So there's going to be lots of different factors in terms of trying to figure out how much money you're going to make. So a lot of things that we care about are functions of several variables. Another example is temperature. You know, the temperature of the Earth's surface is a function of your location. You give me 2 positions, you know, latitude and longitude. So we'll assume for the sake of argument that the Earth is a perfect sphere. It's not quite, but close enough. So we'll assume the radius is constant, so we'll assume rho is constant. You give me theta and phi, I know where I am on the surface of the Earth, and I now have a temperature. Yes?
What about altitude?
We're going to assume our mountains have been cut off. But if you want, you can of course add the mountains and now start going up as well. And then the radius would no longer be exactly constant. But so we'll take the idealized Earth where all mountains, all valleys have been flattened, all oceans dried. Very nice. Okay? How do people present temperature maps? How have you seen temperature maps presented? I've heard somebody say the word begin with a C.
Color.
Color, right? You draw, you know, it's a huge subject as to how do you represent on a plane, you know, something that's not planar like the Earth. So there's the Mercator maps. So you know, if you have something like America, it's not, you know, so bad. You know, the rest of the world doesn't matter. Only continental U.S. matters as well. I don't want to get in trouble. We'll add Alaska and Hawaii. And I was recently in Puerto Rico, so we'll make sure Puerto Rico gets all right? And so what... Is that a question? So what you can do is, one way you could represent the value of your function is, at each point here, I go up the amount of the temperature. If it's 50 degrees, I go up to here. If it's 60 degrees, I go up to here. If it's 10 degrees, I go up to here. Like a pop-up book. Okay? How many of you have ever gotten, a major newspaper that, pops up? Okay, they don't do that. When I was young, they didn't even do colors. They did grayscales. But now they don't mind printing in color. It's not so bad. Color is a great way to quickly represent what's going on. And they use different colors to represent different values. Maybe the darker the color, the warmer it is. And so sometimes they do that. Sometimes they draw lines. And they'll say, this is the 50-degree line. This is the 60-degree line. This is the 10-degree line. Something like that.
Contours.
And these are the contours. And so these would be temperature contours. And I think the correct term is isotherms. It's been a while since I've done chemistry. So constant temperature. So a huge issue in science is how do you present information? Okay? I'm not going to cover the beginning of the chapter where I talk about what is the domain, what is the input set. I'm going to assume you have read the definitions. I want to talk about the consequences. How do we present something? Ideally, when we do functions of one variable, I give you a plot. So for one dimension, functions of one variable, here's my x, here's my f of x, y equals f of x. And I just plot it like this. It's very easy to plot a function of one variable on a piece of paper, on a blackboard. Not a challenge. Plotting a function of two variables is a challenge. I have to have things coming up off the paper, or if I don't do that, I have to use some kind of shading. Okay? And so we're going to talk about now level sets. Okay? So the question is, what is the best way to present this information? What if I had a function of three variables? Three variables were really out of luck. Right? You try to visualize what does a function of three variables look like. You could still do color, but now if you had like a sphere, you'd have different colors inside, and it would be very tough to just look and see what's going on without things getting in the way. One way to represent a function of three variables is to take cross sections, is to slice it. And say, here is my sphere of radius 1, and this is what it looks like. Here's the color. Here's my sphere of radius a half. Here's its color. Here's my sphere of radius a quarter. Here's its color. Okay. So now it's time to do level sets. Level sets. Given a function f, the level set of height or value c is the set of all inputs that evaluate to c under f. Okay, so for example, let's say f is from the unit circle or the unit disk to the real numbers. Then the level set of height c is the set of all points x, y such that f of x, y equals c, and x squared plus y squared is less than or equal to 1. This is what it means to be in the unit disk. X squared plus y squared is at most 1. This is what it means for my function to have value c. Okay? Any questions on the definition? So I have to give you two inputs when you're talking about the level set. I have to give you the function, and I have to give you the height. So I like to use the word height and not just the word value. The way I think about it is think of a three-dimensional terrain. Think of Williamstown with the mountains and the valleys. And then the level set of height c is just all points that are c units above sea level. So if I give you, something like this. So here's my three-dimensional plot over Williamstown. Okay, I apologize for the shady artwork. So something like this. Okay? And let's say this is 0 over here, this is 50 over here, maybe it's 55 over here, and maybe it's 60 over here. So the level set of height 60 would be what? Any point 60 units above sea level? No. So the level set of height 60 would be empty. So level set of height 60 is the empty set. And we denote the empty set like this, a 0 with a slash through it. And so now, as we lower and lower and lower that value, when we finally hit 55, if I've done things correctly, I can always cheat a little bit and make sure I've done things correctly, we just grazed the top of the mountain. And so what would the level set of height 55 be? It would be what? So what would the level set of height 55 be? Yes?
What would be the coordinate where it touches?
It would be the coordinate where it touches. So you would then go down and see what is the xy coordinate corresponding to this. If I now go down a little bit more, if I go to maybe 52, I'm now going to get some kind of shaded in, almost like a circular region. It'll be all those points that are 52 units high. It'll be some kind of closed curve down there. As I keep going down a little bit more, I'll eventually come to the point where, over here, I could actually have two regions, something over here and something over here. Okay? So these are the different level sets. Level sets are going to be a very convenient way to understand a lot of the stuff later in the semester. When we're trying to look at functions, we will be looking at level sets. So again, these are all the points that evaluate to the same place under F. Think of it as all the points that are the same height above sea level. Okay? So the question is, what do different level sets look like? And so I can choose different functions, and we can try to find what the level sets look like. Do I have any? All right, so I'll do the example from the notes. So let's take f of xy equals 4 minus x squared minus y squared. And a good way of looking at this is it's 4 minus x squared plus y squared. So when you look at this, all that really matters is how far you are from the origin. Right? Because it doesn't depend in a bad way on x and y. It only depends on x squared plus y squared. What do you think would be a really good coordinate system to use to understand the level set of this function? So it only matters how far we are from the origin. What do you think would be a good coordinate system?
XYZ.
Not XYZ.
Polar.
Polar. Now, if USA Today gave you a temperature map of the United States of America and converted the map to polar coordinates, okay, this would not really be good. This is not how you're used to the Americas being presented. But for this function, it would be more natural to look at it in polar coordinates. Let's look at it in the Cartesian, okay? I'm not going to change my maps of America. I like how things are laid out. So let's look and see what's going on. When x and y equals 0, what's the value of the function? 4. So this point here is the level set of value 4. So c equals 4. The level set is just the point 0, 0. That's the entire level set. What if c is greater than 4? What if c equals 5? What's the level set? What do you think the level set would be if c is greater than 4? So are there any values of x and y such that 4 minus x squared plus y squared equals 5?
Empty.
Empty. So c greater than 4 level set is empty. And now, as we start decreasing the value of c, the level set becomes an expanding circle. So if I take c equals 3, it's going to be a circle of radius 1. If I take c equals 0, it's going to be a circle of what radius? 2. And let's see how you would solve it. So, solve for the level set of a c less than or equal to 4. So we want all x and y such that 4 minus x squared minus y squared equals c. Well, this is the same, just moving things around, as 4 minus c equals x squared plus y squared, or x squared plus y squared is the square root of 4 minus c. So one of the parts I didn't do in class today was talking about where is a function defined. Okay, so in terms of trying to find out where a function is defined, I have a square root of 4 minus c. When is the square root defined? What must be true? The square root must be a number greater than or equal to 0. So we're okay as long as c is less than or equal to 4. And that matches our intuition. And so this is going to be, this should be the square root of x squared plus y squared is the square root of 4 minus c. So we're okay as long as c is less than or equal to 4. This is the equation of a circle of radius square root of 4 minus c. So the level set is a circle of radius square root of 4 minus c. And so we've completely specified what the level set is. Okay. Any questions about this? So you'll probably have some homework problems looking at ellipses or hyperbolas, because I know you enjoyed them so much in Algebra 2 and you missed the fact that you haven't seen them in a while. These are extremely important shapes, especially in physics and astronomy, for orbits of planets and stuff like that. Yes?
So you have on the board, you just have the circles at the level set 4, 3, and 0.
Right.
But would you ever ask us to like sketch a level set? Because wouldn't it just be like a filled-in circle?
For this problem, it would just be filled in circles. But I could give you something where it's a little bit more interesting.
Yeah.
And so in fact, since my artistic talent is not nearly as good as Kayla, I will shift to the computer. Would you like to hit the button to turn on the computer? You want to come and turn on the computer? What kind of up do you want to the computer? Do you want airplane or just regular up? Okay. I need you to push the flashing red button. Excellent! That's what you did? You turned it on? I was half expecting they were going to clap, but we'll just double that one more time. So here's the function, the sine of xy over 10 plus the sine of x plus y over 10 squared divided by 4. Right? This is a function I really don't care about, but it's good to illustrate. What I'm doing here in Mathematica is I'm controlling here, I'm calling it h, that's my height. And so as I move it up and down, if I move the height too high, you see it's above everything, and the level set is empty. Now as I move it down, I move it all the way down to a number so small, it's below everything. And now as I just move this up, as it intersects the region, it'll give you all those points at a given height. So if I move it up like this, you can see now down here it's giving you these points. And as I keep moving it higher and higher and higher, if I do it just right, you see there's this valley over here. I can move it up so it just hits that valley. Move it around. Something like that. and then I can move it higher and higher and higher, and you can see which points it's hitting. That's what the level sets are. Just imagine you have this plane, and you're slicing it, and you're finding out which points are that height above. Okay? That's the whole concept of a level set. You're taking a region, you're taking a surface you care about, something you want to study, and you're splitting it up into easier parts, into parts that all have a common value. So, I'm looking at a function. It has inputs, it has outputs. And what I'm saying is, I want to sort the inputs based on their outputs. So if you want, I will sort people based on, do they go to a public school or a private school? When I'm trying to figure out whom should we accept to Williams, I want to take into account maybe what opportunities, what access have you had. Maybe I'll sort people based on financial status. Maybe I'll sort people based on what sports team they root for. For the most part, admissions does not talk too much about that last one. But I can sort you based on different things and then compare. And so I want to look at all the people that have had a similar opportunity. I want to look at all the outputs that have a similar value. All right, so this is what we would do for level sets. Here's a contour plot, again, level sets of the function x squared plus ay squared. X goes from -4 to 4, y goes from -4 to 4. Let's take a equals 1. If I take a equals 1, what shape should that be? X squared plus y squared, what shape is that?
Circle.
A circle. And so if you look at this, I'm plotting basically the level sets. And as I go further and further out, what do you think is happening to x squared plus y squared? So over here, the value of x squared plus y squared is 5. Here it's 10, 15, 20, 25. So these are the different level sets. I can change the value of this number a. I could make it, let's make it 0. 0 is a good choice. Is this surprising or not? So my function now becomes x squared. Does y matter? Does y control the value of the function? No. Actually, I could probably have drawn this one. This is within the realm of what I can do. And so if you look over here, this is a value of 2, 4, 6, 8. And over here, you'll have symmetrically 2, 4. So if I want to look at the level set of all things that evaluate to 2, well, if a equals 0, I have x squared has to be 2. So it's going to be all points whose x-coordinate is square root of 2. That's a vertical line. So here, the level sets will just be lines. If I make a be negative, so I'll let it be -1. Alright. So if I take -1, what kind of shape does this look like? X squared minus y squared. That's a hyperbola. So if I take x squared minus y squared equals 0, that's a special case and I get 2 straight lines. So the 2 straight lines here are coming from a level set of 0. Could I have a level set that's negative for x squared minus y squared? So could x squared minus y squared be negative? Yeah, take y greater than x. Could x squared minus y squared be positive? Yeah, take x greater than y. So this is the first example where for every value of c, the level set is not empty. I don't know if that makes you feel better that there's at least an example where every value of c can be realized, but here it is. Alright? Do you think the ones up top are the ones where the c is positive or negative? So here, which is larger, x or y?
He was going to decide that.
Y is larger, so I would guess there that that would be a negative level set. And so hopefully, yes, -5, -10, -15. Over here, +5, +10. There's not time today to do planetary motions and circles, so I will save that for the future. Alright. So everybody except Kayla, I will see you later. Kayla and I will be at mission at lunch at noon today, and we will try to be at mission for dinner at 5:30. If you're just dropping office hours, feel free to shoot me an email as well. I need to hit the button again.
Taylor,
Do you want to do the upgrade?
Looks like Sunday was.
Oh, did you say to hit stop? Oh, did he stop it?
I think
You want me to stop it?
Oh, yes,